All right, everyone, we're going to go ahead and get going. We're hoping some more people jump on as we get going. Um, if you're here, make sure you open a chat window and just type, type your name, who all's attending. So in case you have more than one person at your camera, for instance, I see Morris and Anthony look like they're on the same device. So they could say Morris is here, Anthony is here. Um, we're going to start with our Toolbox Talk. This is the little weekly safety meeting we're supposed to be doing. This topic is whose responsibility is it? So, after an accident has occurred, it is not unusual for those who are around the injured worker to feel guilty. This guilt is part of each person's inner awareness that there was possibly something they could or should have done to prevent the accident. Sometimes the accident is the result of someone else's mistakes, but who caused the accident is not as important as who is responsible for the accident and what steps will be taken to correct future similar accidents from happening. The following is a partial list of responsibilities for safety on the job. Um, so some responsibility rules that applies to everyone. If it's unsafe for you, then it's unsafe for the next person, and the hazard should be corrected now. The next point is safety doesn't belong to any one construction craft. Rather, it's part of every construction craft to be responsible. And if safety doesn't begin with you, it won't begin at all. Now, there are some responsibilities that apply to each individual. An individual's responsibility, they have responsibility to themselves, they have responsibility to their family, to their coworkers, and to their companies. And then remember, workers' compensation checks won't pay all the bills, nor will they replace the self esteem one has from being a good provider to their families. Without complete cooperation from everyone on the worksite, it just will not be as safe as it should be. A note to remember always promote. Oh, sorry. Sorry, I wasn't supposed to read that note. Okay, that's all we have for the toolbox discussion topic. If anyone has any questions or something to say about it, I would say go ahead and do that now. Mike, did you think you wanted to add? All right. Okay, then we're going to move on to our topic today, talking about switches and relays. First, we're going to talk about just simple switches, and that'll help us understand relays when we get to that point because a relay works the same way as a switch with an added component. First couple little definitions we need to know about it is an open circuit and a closed circuit. That open and closed terminology is very important to understand uh, for understanding switches and relays. Over on the right hand side, you can see I have a kind of a visual representation of an open circuit. You can see there's no connection between the two dots. That switch leg is flipped up with that a gap there, so the electricity won't be able to pass through that. And then below that, you see a closed connection where that switch leg comes down and there is now a solid connection from point to point on there. Um, and then a couple more points of terminology we need for this topic is we have poles. You'll see switches described as either single pole or double pole, or potentially even more than that. But in our cases, they're typically single or double. And then you'll also see them described as throws. A lot of times these are abbreviated to just the um, initials for the abbreviation. So you'll have like SPST on that top switch. It is single pole, single throw. A common example of a single pole, single throw switch would be like your light switch. You can see that there's just one point of contact that that switch can land on. Um, Another thing that works that way would be our typical manual pull stations, like our conventional pulls. They just have a common and a normally open. That would be a single pull, single throw switch. And when you pull that pull station, that switch then closes. There's no other action that happens, no other circuit that is involved or affected. So pole indicates the number of circuits that one switch can control for one operation of the switch. So if you have a double pole switch, then it's affecting two circuits with one manual operation. And then a throw indicates the number of contact switches. So if you look at the second image we have down there that has the 3 terminals, that is a double throw switch, but it's still single pole, because you have that A is one input coming in, but it can go between 2 different potential outputs, being contacts B and C there. So that would be a single pole double throw switch.
Zoom meeting going on now.
Okay. Yeah. Another thing to see at the that bottom right one, where you have A, B, and C, these are what's called dry contacts. This will relate back to the example we've been using with the water hose. If you think of wet, the water being the electricity flowing through, then having dry contacts mean that there's no voltage here. We're not supplying power. These contacts have no power built in them. They're dry contacts. And then we will apply electricity from an outside source. You won't typically see them labeled A, B, and C like this. More commonly, you'll see them as common, normally open, and normally closed. The A in this case would be your common coming in. And then B down there would be your normally closed, because when that switch is in its normal position, nothing is acted on it. There's been no outside force that's forced it to change. That B contact is normally the closed circuit. Now, whenever you act on the switch and you put it in its not normal state, it is no longer a closed circuit. But when it's in normal state, it's closed. So it's normally closed. And then that C terminal is just the exact opposite. It's normally open. And then when you physically act on that switch, you toggle that switch, that lever then moves up to that C terminal, and the open contact, the normally open one, becomes closed because it's no longer in its normal state. I have, well, hold on, now it's not working. There we go. I have here a little circuit diagram that shows a basic function with a single pole, single throw switch. And you see that abbreviation SPST. That is always going to mean this type of switch. And that'll also carry over to relays. So if you're looking at types of relays and you see it described as an SPST relay, then it has this same type of switch built into it. But you see there's a power source over on the left-hand side. It flows up and through the SPST switch over to the light and then back to the power source, making a complete circuit. Now, right here, this is drawn where that switch is open, so the light is turned off. If we would close the switch, that would turn the light on. Our next example here, we have a double pole, double throw switch. So now you see we're back to those A, B, and C terminals. Remember, A would be our common, B right now is our closed, and C is our open. I don't know if this switch is in its normal or not normal state, but we can see that the lamp on top is turned on and the lamp on bottom is not. And if you follow that switch, you see the switch leg is pulled over towards terminal B, closing that side of the circuit and leaving side C open, which is why the other lamp is turned off. And see, this is still a single pole switch, so it's only one circuit, but it is also a double throw, meaning there are 2 possible paths for the power to go down. The next most common time we're going to talk about is a double pole, double throw. And so now you can see there are 2 sides of this switch. You have the side 1P and the side 2P over here. And those are 2 separate circuits that are not connected to each other in any way. A common example that we'll use of this is when we change out the little switches in our pull stations for access control purposes, we change them from a single pole, single throw switch to a double pole, double throw switch. And they, instead of having just 2 wires come off the back of the switch, you'll actually have 6. two sets of dry contacts that are, again, not related to each other in any way at all. So you'll have common one, normally open one, and normally closed one that all work together. And then you'll have common two, normally open two, and normally closed two that only work with them. And the point of this is that one side we can tie to our fire alarm system, so the pull station still puts the building in alarm like it's supposed to. But the second side, we're then able to interrupt the power to a mag lock by using that second side of the double pole, double throw switch. Did you have? Okay. And that's really all there is to understand about switches. I'm going to move on to relays now, unless somebody has a question. Maybe you're caught up about something, or you want to know something specific about switches before we get into relays.
Yeah, can you hook that up backwards?
Yeah. With dry contacts, there's no polarity specific anything, because it's literally just power flowing through a switch. So whether you hook it up over here on this side or right here at the 1T terminal, it's the power is going to flow across this same conductor. There's not a positive and negative.
Well, there, excuse me, there would be an exception to that. If you needed that common on the common side, then you need to know where your power's coming from, whether you're switching the positive or negative. So you would want your power feed on the common and not necessarily on the normally open, especially if you needed to use the power either way. In other words, if you needed something to be powered up most of the time, or something to be powered up only when it was when that switch is open. So you really need to know where and I think he's going to get into this in a minute. You need to know which side is your line side and which side is your load side. Line side.
Yeah. I was just going to ask that, but all right.
Okay.
Yeah, we'll talk about line and load in a little bit, because I have the elevator recall example you requested, Ramsey. And so that's actually what we'll end with today. And I'll get into line and load when we talk about that.
All right.
To kind of give you a visual of what Mike was talking on, right here is our power source. And so he's talking about knowing the line that's coming from our power source. And this would be common right here, because it's the only one that has common between both points. So if in this case, we need both B and C to do a function depending on the position of the switch. So in this case, it's important to make sure your line goes to your A, not to your B or to your C, to then be switched through A. In the case where if you're using a monitor module and you're just monitoring a set of dry contacts for a switch, like maybe it's a conventional pull station or a sprinkler device or a conventional duct detector, in that case, knowing which one is normally open and common, positive and negative wise, doesn't matter so much. But in the case of having a circuit that performs a function, it does. Does that answer your question?
Yes, sir.
All right. Is anybody have anything else before I move on to relays? All right, I'm going to go ahead and move on. So the main difference between a relay and a switch is the way it's activated. The switch, like you can see in this picture, is obviously manually activated, most likely by your hand or your finger to just toggle it on and off, just like a light switch on the wall. A relay is powered or switched rather by an electromagnet. And so right here, I have a picture of a very, very simple electromagnet. If you wanted to go home and build this in your garage just to test it out, it's very easy to do so. All you need is a battery. This example shows a 9-volt battery. You can also use a AA or a AAA or whatever you got. The different voltages will vary in strength, but then you just need some scrap wire and something iron to wrap the wire around. In this example, they're using a nail. If you don't have a big enough nail to try this with, you can also use just a regular screwdriver. And you can take that and you just wrap the coils around and around and around the nail. And then you connect your positive to one end of the wire wrapped around and your negative to the other. And your nail becomes magnetized. And then as soon as you remove power, the magnetism goes away or weakens significantly. This is very similar to how the primary side of a relay works. Another real quick, just kind of tech tip. If you're working with something and you have a regular screwdriver that's not magnetized, but you need it to be magnetized, maybe you got to get a screw back into a hole somewhere and you can't fit your hand in there and you need that screwdriver to hold on to that screw on the end of it, and you've got a battery and a short little piece of wire, you can do this and it'll temporarily magnetize your screwdriver. And then if your screwdriver is magnetized, a normal screwdriver that's magnetized, and you don't want it to be anymore, just take it and whack it a few times on the top of your ladder and it'll scramble the molecules back up. They won't be magnetized anymore. Now, if it's not a regular screwdriver, it's one that came from the manufacturer as a magnetized screwdriver, this doesn't apply to it at all. This is just for if you have like the cheap Harbor Freight or Home Depot regular plain Jane screwdriver. Just a real quick little tool. But right here, when we look at our relay, these are single pole double throw relays, just like we've been talking about with the single pole double throw switch. You see we have our common, our normally closed and normally open, but now we've added a second component there at the bottom. You see where those wires are coming in and making that coil symbol? That's that electromagnet that we just talked about. And what happens on the picture on the left, this is normal condition, no voltage is going into it. So you see the normally closed one has that leg over to it closed. There's actually a spring that sits inside this relay from here to here that pulls this leg this way. And it's just weak enough that when you do apply voltage, like over here, the magnet pulls it down this way, overpowering the spring. And then as soon as you turn voltage back off, the spring will pull it back. This is how a typical conventional relay works. The reason we do this side over here, your primary side, has no physical contact with your secondary side. So we're able to control much larger circuits with very small or low current or low voltage circuits. So in the fire alarm world, that's really handy to us because all of our stuff is low voltage, but oftentimes we have to interface with higher voltage things like smoke dampers, elevator shunts, air handler shutdown, and I think there's another one. I'm drawing a blank.
Doors, door holders, all kind of stuff.
Yeah, all kind of stuff. So,
Hey,
what's up?
hey, Keith.
Yeah.
This is Royce. Hey, what kind of resistance were you read on that coil so you know if it's coil actually good?
It should not be a direct short. Like, I don't know an exact number, and it probably varies from coil to coil in each different manufacturer's relay. But if you see a direct short, you know, something like 0 ohms or 1 ohm, something like that, that's going to be bad. That means that coil is shorted out and it's not going to, it's not going to work. And then if you see something that's completely open, like that OL or something in the mega ohm range, that's going to be too much resistance. So now you have an open connection.
Right.
So it's going to be somewhere in between those two, but I don't know exactly what it is. Right now, Terrence and Mike are running to grab an MR101, and they're going to put a meter on it so we can get an answer for you for that, Royce. But while we're doing that, I'm going to keep moving.
All right.
So right here, we have an example of a circuit where our primary side is a small 9-volt circuit with a switch, and our secondary side is actually a 230-volt high voltage circuit powering some kind of lamp. So a reason for doing this might be that this switch right here that they have on some kind of control board might not be able to handle the 230 volts flowing through it or the kind of current that this lamp would require. It might burn this switch up. A real common everyday use for this that we'll all be familiar with is our cars. Our headlights do something like this. There's a very low current side just flowing through your headlight switch that's on your dashboard, and then it goes through a relay, and then you have a much higher current side. Even though it's the same voltage on both sides in a car, the other circuit is a much higher current, and that's able to power your headlights, where the headlights draw so much current, it would actually burn up the switch that's on your dashboard. In the fire alarm side of things, like I talked about, we work with a lot of 24-volt systems, but we're having to control 120 and 240, and sometimes even have to deal with 480. And so relays allow us to have a safe interface with that, where we can use our lower current, lower voltage control circuits control much more powerful things. And so again, I want to just mention it over and over again, really make sure it makes sense. The primary side of the circuit in no way is connected to the secondary side of the circuit. So when you're working on your fire alarm circuit, where the primary side typically, you should not see high voltage from the secondary side crossing over to your primary side. That means something's wired wrong, and you need to correct that before you connect those wires to any kind of control panel or other devices, because that higher voltage will mess up all of our other devices.
I need to use the meter. I can't read this one. Get in the truck.
Okay, so before I get into the elevator recall, is everyone still with me on how these relays work different than switches? Okay, I'm going to go ahead and move on. I'm going to take no answer as we're all good. So elevator recall. This confuses a lot of people, and it's real easy to forget if you don't do it every day. This drawing that I have on here is the same drawing that I put on every one of our detail sheets for every single job. And I'm going to explain what the different parts are going on here. So the first thing to understand with elevator recall is we have two separate functions going on. And I think that's where a lot of people get a hang up going on, is we don't necessarily process that there's two separate things. So I'm going to start with the more simple of the functions, and this one is shunting the elevator. Now these power shunts for these elevators kind of work like a giant relay. And so there's 480 volt passing through the secondary side of it, and then there's the primary side that acts as the small control circuit, which is actually the 120 volt that we control. And what happens, that 120 volt flows through a small electromagnet that pulls a giant disconnect switch off the 480, killing power to the elevator. Now, if they just wire nutted it together and they didn't pass it through our relay, that shunt would always be activated and that elevator would never work. So what we have to do is we have to break that circuit and give them a control switch on and off. And that's happening over here with our AOM2RF. This is the Gamewell part number. The Fahrenheit part number would be IDP relay. I'm not familiar with what like a notifier part number would be or some other brands. But whether it's an SK relay, IDP relay, or the AOM2RF, they're all the same part. They're just for different brands. You see this line right here, this would be our line. This is our power coming. I have it labeled as 120 volts AC, hot from electrical panel. So this is coming from the power source. It's real easy to remember that line comes from the power source because you think that the power lines bring the power to the building. The line in this case brings power to our device. So that's what line is. And then it comes here in this normally open. Now we're going to ignore this other leg here for a second until we talk about the second function. So we're going to go right here from our line. It's in normally open, and it stops right here until we switch the condition of this relay. Now this is an intelligent addressable relay, so it gets switched by control programming, and it has a slightly different way of working than the electromagnet, but that's not important for our purposes. The dry contacts on it still work the same way. And I just noticed, I'm going to have to fix this in my drawing. This is labeled as normally open 1, and then I have another normally open one here. That's not real. This should be normally open 2. So I need to fix my drawing. That's an error.
Yeah, I was gonna say that.
Well, good eye. So we're coming in here to this normally open 2, even though it shows 1. And then it stops there until we switch the condition of this relay. And then it jumps up right here where I have it coming out common 2. Now, from what Mike was talking about earlier, this would actually be wired backwards from what he said, because he said come in on the common and leave on your normally open and normally closed. And that's a good practice to do. I drew it this way because it makes the drawing a little cleaner and you have less lines crossing over each other. In this case, it'll work either way, but it's very important to know which one is your line and your load because of that second function we haven't gotten to. And so right here, coming out of common 2, going up this way, you see it's 120 volt AC hot to shunt. This is going to that electromagnet I talked about. So this is the load on the circuit. So you have line and you have load. The line comes, it's the power source, it's the power line coming to the device. The load is the thing you're actually powering. When you talk to the electricians wiring up shunt trip, it's important to know which one's the line and the load, because now we're going to get into the second function, because this is all the first function is. We're just going from normally open to common, so we can turn that electromagnet on and off. The second function is we need to monitor this power circuit for constant power. We need to make sure it's always powered, because if the circuit loses power for any reason, that means this emergency function won't work correctly. So we have to make sure that 120 volt is turned on. And if for any reason it gets turned off, we need to let the building owner know, hey, there's a problem. This needs to get fixed because you have an emergency function that won't work unless this is fixed. And so that's what this business over on this side of the circuit's all about. We're just monitoring to make sure this line is always hot. So if you look right here, if you can see under that normally open 2, I'm going to keep calling it normally open 2, where the line comes in, under that same screw terminal, just the other side of the screw, I still have the 120 hot from electrical panel. This is the line coming over and powering the primary side of our MR101 relay. And it's important that this lands on the line, not on the load, because we want this MR101 to be turned on as long as the circuit is turned on. We're not worried about it turning on when our relay changes states. And that's what would happen if you put it on the same side as the load. If you put this power circuit on the same side as the load, the MR101 would only change states every time we activate our relay. And so it wouldn't work correctly. The other wire you see coming over here, this is the neutral. When you get into higher voltage, like the AC stuff, they don't call them positives and negatives. They call them hot and neutral. There's a lot more technical difference between them than that, but for our sake, our purpose, just treat neutral kind of like the negative. We don't need the neutral at all for that first function that I was talking about, where we actually trip the shunt, but we do need neutral to make sure our relay power is on correctly. And then from there, it just goes to the shunt with the other side to help power that electromagnet that kills the 480. And so that's all the neutral is doing, is powering the MR101. And that completes our primary side of the MR101, which is the input that can, switches on and off. And as long as this circuit has power, the MR101 stays on. And there's a little red LED somewhere around right here on the MR101s. It should always be lit. If it's not lit, then your circuit doesn't have power. And then the other side of the relay is up here. You see we got a normally closed, a common, and a normally open. And I drew this side backwards too. That's another thing I'm going to have to fix about this drawing. When this relay is not turned on, it sits this way. This is normal condition whenever it's powered off. So from common to normally open will be open when the relay is turned off, and from common to normally closed will be closed when the relay is turned off. And that's how that closed terminal here is how we make the alarm signal. See, I said supervise with AMM2F. That's the game wheel part number for the monitor modules. The IDP mini-mons and the SK mini-mons are, again, the same part for different brands. So we actually need to go from common to normally closed. So I'll fix that too for my drawings that go out in the future.
What would be on the normally open? You got that label? You got that on the normally open?
It's on the normally open because
that's correct. That's where it should be.
That's where it should be if we wanted it off. If we want it on, it needs to be on the normally closed because it's no longer in normal state. The normally closed would actually sit open.
But when you power that relay up, it's going to go.
When
your normally open is now going to be closed.
They're going to have to put you back in the field, Mike. That's wrong.
It's common and normally open. And
yes, it's
but both of them can't be normally open.
Relay is turned off. Right. It closes when you turn it on. So this would always have this in alarm.
Oh, yeah. Listen to Keith.
There's a reason I'm doing the class and not Mike. No, I joke. I've run everything by Mike for the most part. But yeah, so I'll fix that on the drawings coming out. But what happens is this right here is open between your normally closed and common while your relay is powered up. So that means that you read the resistor across it, which is what your monitor module wants to see to stay in normal condition. And then when it loses power, those terminals short out, and we program this as a supervisory. So it enunciates that there's a problem out there in the field. Yeah, it shows that there's a problem out there in the field, and it lets the owner know. So that's what the point of the second part of elevator recall for, is it's just monitoring for power loss. There you go. Now you drew it in the right spots. Okay, I think I've explained this pretty well. Is everyone still tracking with me? Is there any questions about this? All right, I'm gonna take that as a good.
Hold on.
Okay.
The other neutral you was talking about coming off the MR101, where does it go?
So what I've seen when I've been in the field, they typically only bring just one neutral to us. They don't bring us like an in and an out for a neutral. So in that case, you would only land it on the MR101. But in this drawing, just in case they brought you 2 white wires, then I showed it to where it goes, it's going to the same places where your load goes.
All right.
Because all it's doing is it's providing a negative to complete the circuit, powering the MR101. Another thing I've experienced on these MR101 relays, electricians use a lot larger wire than us, and so you can't always get both the legs of wire under that 0 terminal, so you might have to make a pigtail where you use a wire nut to bring the 2 together, and then just have a short little jumper that goes from the wire nut, so you're only letting one wire.
All right. Calvin, when you get up.
Okay, is there anything else?
Remind everybody to sign in.
Okay, and just one more time, I want to remind everyone, use the chat feature in this to make sure you sign in. That way we can use it to keep attendance. And one last thing, just to remind everyone, your 2RF, your addressable relay over here, that's the side actually controlling the shunt. Your mini module and your 101 are just there to supervise for power loss. So if that's everything, then again, make sure you sign in, and y'all are free to go. Thank you for being here.
How you sign in?
Just send us in the chat. Just say, hey, Ramsey was here.
All
Don't
right.
worry, we know you were here. You talked to us.